father, son.
Okay. 11 is really 10. Probably 12, but maybe something completely different.
Or you could really wait for what they
There we go.
Well,
That's
Windows
bothers
13 will never go because of superstition.
Little
So
sus.
that's
there's actually like legitimate office buildings in the actual real world that
No,
have floor
13.
12.
Yeah, like there's a lot of places I used to live, it went 12 and then 8. It was literally the same.
It was the 13th. Oh, the penthouse was on the 13th floor?
Yeah,
Yeah, that's
so they
just poor
named it
planning.
key. Yeah.
That's just poor planning.
Well, the pen is no different, they just named it that way.
Oh, it's not even a penthouse suite.
Yeah,
It's
it's
just like every other floor.
I just,
So hard. You live on the roof now.
Yeah, there you go.
Malcolm, across the printer.
just trying to figure out how much money got wasted.
Define waste.
Wasted as in there's cutters way, way.
Good.
Happy Kids Day. Today's Kids Day. Kids Day in Brazil.
What day?
Kids Day.
Kids Day?
Yeah. For kids Brazil, today we got some gifts, some presents.
That's like Christmas in October or
You are
something?
like your kids.
It's like Christmas.
So-
Yeah, there you go. Christmas in October. Yeah, when I was a kid and I really wanted like a more expensive gift, I would negotiate with my parents and say, look, you don't need to give me anything for Kids Day. And that accumulates for Christmas. I'll get my bike, something more expensive. Yeah. Negotiating skills, right? Okay. So today we're going to continue on the topic of functional programming. We started this topic last Thursday, when we talked about lambda functions, right? Lambda calculus, right? And we saw that you can think of lambda calculus as a computational paradigm, or formal way of describing computation. Just like when you were in theory of computation, you studied Turing machines, right? You studied state machines, and you were able to describe using those formal models of computation that you can describe. Of course, in say a much harder way, but you're still able to describe computation using those models, right? The same goes for lambda calculus. And some of the things we discussed when we were talking about lambda calculus, you will be able to identify in modern in modern programming language that support functional programming. Hopefully, you will be able to see those similarities. So, what are the things that make a programming language to fall in the functional programming paradigms? What are the things that we commonly see when we discuss the functional programming paradigm. So the first thing is that when we look at functional programming, functions are first class, right? So different than most programming languages, programming languages that support the functional programming paradigm treat functions as first class. So they can be, for example, passed as arguments to other functions, right? So you can pass a function as you would pass a value, right, as an argument to a function. That's very powerful because you can, for example, define a function that is incomplete, right, or very generic, and the piece that is missing or how you want to change the way your function behaves is based on the function you're going to pass, right, as an argument. That's very powerful. I don't know if you guys are seeing the implications of having functions pass to other functions as arguments, right? That's different than when you have a function calling another function, right? Because that's very limiting. When you have a function pass as argument to another function, you're kind of like changing how the function behaves based on that parameter. And you can also assign functions to variables, so you can use aliasing like you were used to when you assign a variable to another variable. So then, well, it's a, think of like if it's a reference type of variable, you have an aliasing, right? You have two ways to accessing that object referred by the variable. Kind of similar here. If you have a function assigned to a variable, you can use the variable to call the function as well. So that's the first thing. You can create anonymous functions. So anonymous functions are sometimes called lambda. So this lambda is different than lambda calculus. It's basically, lambda is also synonym to a function without a name, right? That's more into what we usually think about lambda. When you heard lambda in computer science, you usually think about unnamed functions, okay? So look at this function. So function reduce left. What is this function is doing? This function takes, see the parentheses, right? So this function is being applied to a list, right? 0 to 10 is a list that goes from 0 to the numbers from 0 to 10. And then this function is being applied to this list, but it takes a parameter. The parameter is another function, right? But I just want to create this function on the fly. I don't want to first create the function and then call reduce left. No, I just want to call reduce left, and as I make the function call reduce left, I need to pass a function that will tell me how am I going to reduce, do a left reduction operation on this list. And I'm going to do that by creating a lambda expression that tells how this list will be worked, right? And basically this function takes two parameters, and the result is adding those two values. Okay, so this is an example of a lambda expression or an anonymous function because I don't see a name for this function being passed to reduce left. So this is an unnamed function, lambda expression, typically used in functional programming languages. Functional programming also typical programming language that support functional programming. They provide a way to combine functions through function composition. So as you see here, we have function f, function g, and then we can create function h by combining functions f and g, right? So the result of function g is going to be passed to function f, right? Special functions, basically those functions are generically called predicate functions. Basically, if you have a function that returns true or false, we'll say it's a predicate function. Here are some examples in Scala. Function even returns a Boolean whether the x parameter is even or not. In function greater than, it will tell if it's a function that takes two parameters and returns also a Boolean, whether based on the first parameter is greater than the second. This is in currying notation. Functional norms, that's a synonym for higher order functions. So you have some type of norms here. This is the apply to all function norm, which basically map. It's also a higher order function, also applied to a list. Many of these functions we're going to discuss more details, but map is a function that expects also another function passed as parameter, and this function will do a transformation on the values. Okay, so imagine that you have all these functions. For example, if I apply function f, right? If I pass function f to map, basically I will be adding 2 to each of the numbers. If I apply function g, I will be multiplying 3 to each of those numbers, and so on. Functional programming also favor recursion over iteration. Okay. Here's kind of small. Let's see. You have two versions of map. Okay. So this first version here is basically it's non-recursive version, right? This is the recursive implementation of map because we check if the collection is not empty. If the collection is not empty, we apply the function, the given function f, to the head of the collection, and then we recursively call the map to the table. So just showing that how it's just saying that we're going to see many functions in functional programming being implemented using recursion. It feels natural to use recursion when we work in functional programming. Doesn't mean you have to do that. What else? A well-designed functional programming language provides a set of primitive functions and data structures, especially when it comes to working with collections. Okay, so those are some examples of functions that we'll be discussing, and these functions are, you can think of these functions as tool functions or helper functions that you can apply to many different cases, and the difference will be how you're going to customize these functions, right? Because these functions are higher order functions, and they require another function to be passed as argument, and depending on which specific function we pass to those generic functions, they will have a different effect on the collections used. We're going to see examples of how to use these high-level functions. So lazy evaluation is also a feature you're going to see many functional programming languages. It's the idea of postponing the evaluation of expressions until they are needed. So in the first example here, you have a collection, and then you're going to call map. Basically, this underscore here is called anonymous variable or wildcard, and just this will represent one of the values being taken from this collection. And basically, this function that we pass in here will be adding one to each of the elements, right? So this function will be applied immediately. But if I do this call here, but differently, I'm adding the keyword lazy, okay? So lazy means what? Don't evaluate this function right away. Only if I try to use alt v2, then the function should be evaluated, okay? So this example doesn't give justice because I have only, it's a small collection. But imagine that this collection is really big, and I don't want to, I don't even know if I need this to be evaluated right away. So I can use lazy, and I can postpone the actual evaluation of the function when this is actually is needed, okay? So lazy evaluations are very useful. We're going to see other examples. Sometimes, depending on the programming language, you can create unbounded collections, right? For example, Haskell allows you to create unbounded collections. So when you have situations like that, of course you want lazy evaluation. Lazy evaluation is almost implicit, right? When you have unbounded collections, because they keep growing, right? And you don't want to evaluate that because it will take forever, right? Something that is unbounded. But you want to consume one at a time. So in those cases, lazy evaluation makes total sense. Here's another example of lazy evaluation. Yeah, so this example is in Scala. there you go. It's showing you an example of unbounded collection. So using from, you just define the start, and I guess because you didn't specify the step is assumed to be 1. So NN is the natural numbers. Okay, so it's an unbounded collection or infinite collection. Of course, because of the laziness, the laziness feature, this is just a definition of how this collection is actually built, right? But the collection will not be created until when it's actually needed, right? And what we're doing here is saying how many we want to take at a time, right? So take 10, right? It will make from, right? Evaluate and return 10 elements of that collection from 0 to 9, right? And I can do things like, in this case here, I want to use the filter function, also a higher order function. This is how I want to filter, okay? And I will take 10 of what I'm filtering here. So filter, because I'm taking 10, I'm only gonna generate from 0 to 18, right? I'll actually generate from 0 to 9, but because the filter is telling me that I should only take the even numbers, right? That goes to 18, right? So those are the actual 10 numbers that I will be taking because of this filter is requiring only even values. You can understand that to define functions like the from function that builds unbounded collections, you have to create what they call lazy list in Scala. So this is a lazy list, and const is the constructor of the lazy list. We're only giving the start from, that's how you get the next value is going to be start plus 1. And you can see this is a recursive definition. Okay? Don't worry about fully understanding the code, the syntax. Don't be specific about the syntax because you will be running these pieces of code later. At this point, I just wanted to give you a high-level view of some of the features that we'll be talking about. Pattern matching. Okay, so this is also something that we will see in, for example, in Haskell, in Scala as well. A way to ability to define a function based on how parameters are matched to arguments. Right, so I'm going to define the factorial of n, and I'm going to say if n matches 0, that's 1. If not, so that's the wild card here, I will do the recursive call here. Something that pattern matching is something powerful, and you're going to see that in other examples of functional programming languages. This thing about function purity is just saying that functions in functional programming language, they should be like functions in math, in the sense that if you pass the same arguments, you should expect the same return value. And the function should not have side effects. So that makes you think that all of the functions that I write, they are pure, right? Well, sometimes, remember, those functions you wrote that use some external value, right? Global variables, Of course, those are not good practices, but just keep in mind that this can happen, right? So for example, look at these two functions here, right? The first one, I'm calling the mi pure passing 2, okay? So because the implementation, how this function was defined, this function depends on this global variable y, okay? And I'm calling the function using the same argument 2, but because 2 is not greater than 3, this call will return, in this situation here, this global y defined this way, the function will return false. But here, just because I changed this global variable, of course, the value returned will be true. So this function is not pure. This function is super dirty, right? It depends on this y, it shouldn't. But this is obvious, right? How would you write something like that? Probably not, right? So in that sense, function purity is not a big deal. But when it comes to I/O, that's different because, and that's maybe the big distinction between more pragmatical approaches to function programming and more strict implementations. For example, in Haskell, we're going to see a little bit of Haskell. Haskell is much more strict when it comes to function purity, and will create, in my opinion, more complexity just to work around functions that require to do I/O, so they will remain pure. Okay, we're going to see examples of that. So there's a bunch of extra complexity, something called I/O actions, just to preserve the purity of the functions. Okay. But Scala doesn't have that, so you can do things like that in Scala. And the thing is, you will argue that people that are more strict in terms of functional purity will say, well, this function greet is not pure because it has a side effect, which is changing the output of the monitor, right? That's the side effect. So the function is because of the I/O, is communicating externally. Okay, you guys understand where I'm going with this? So technically, they say, oh, Scala is not function programming because you can do things like that. Okay, in Haskell, you can't do. You have to use also other things specifically just to do I/O in a function. Okay, but I'm not as strict, so I would say this is, I don't know, it's kind of going too much, carrying the concept too far. Okay, and then I'm starting some examples using Haskell, but before that, let's get familiar with Scala first. Okay, so we're going now to look at Scala's functional programming features. So let's go to resources, Scala guide, and functional programming section. So I don't have slides for those because when it comes to specifics of a language, I prefer writing text like tutorial-like text like this one. So let's take a look here. Function programming is a method of program construction, emphasizing functions rather than commands. We already talked about that. We're going to build definitions as in expressions using the computer to evaluate them. So look at the function add defined in Scala. Okay, so this is in the traditional way of defining the parameters. So we have function add with two parameters and equal. After the equal, that's when you write the expression that kind of implements the body of the function, right? That's the body of the function. So we can evaluate the add function by passing values 2 and 3, for example, which results in 5. So that's pretty basic. Different than most languages, in Scala we can use functions just like we use expressions. So we can assign a function add to a variable and use the variable to invoke it. So for example, I want to assign the function add to variable f. Okay? So add is just the name of the function. And I need to specify that this function takes one parameter. So I don't want to use any specific name for those parameters. It doesn't matter. So I use the underscore as a like a unnamed variable for the parameter. So I'm going to assign add underscore to f. Okay, so f is basically, at this point, f is an alias for add. I can use, I can call function add now using the alias, using f. Okay, so I can basically, and this is the same thing, okay, but I'm using explicit type to define variable f, right? So this is implicit. The type of f is implicit because the type of f is going to be the type of the function add, and we know that the function add f has this type here. Let's learn how to read function types. So because function add takes two parameters, so this is how we express the parameters for function add, right? This function add takes two ints, so we put just the types, we don't need the names, okay, when specifying the type of a function. So int, comma, int, and then we have the arrow. So the arrow separates parameters in return type. So the return type for function add is int. And this is, I'm just calling function add, but using f. Okay. So the underscore is just a wildcard symbol to replace the parameters of the function. Why don't you guys create a project in Scala, okay? I want you to define function add and write a simple program that just assign add to f, for example, and then you make the function call using the f name. Just to practice, get yourself familiarized with Scala function definition, typing, functions. project can be an idea project, Scala project. Have to be SPT. Can create an object class if you want. So you just type main and tab out of completes variables. I don't know if you know that.
Okay. Scrap this. Look at this. If you do, instead of assigning, just add with the wildcard. If you assign add two, so two is the first parameter, right? Then the second one, you want to leave it open. So now, when you call f, you just need to pass the second parameter. Okay. You can see it's almost like functional programming is inviting you
to create other functions from previously defined function, right? You start with add, which is a very simple function that takes two parameters, and pretty much creating a new function f, right? That is like add, but I'm only adding. I just need to pass one value, and it's always going to add the value to 2, right? So it's a more specific or restricted add function. It always adds a 2, right? To something else. So to see the type of a function, so the function add, this is the type of function add. You can see the type when you look at if there's a way to show the type add. Not the parentheses. We'll be able to see the types later. Wow, I was inspired here. I was writing this. Understanding function programming requires you to bend your mind really a little bit. Think about functions, either arguments or return values to other functions. It's almost like matrix, right? Okay, higher order functions. So a higher order function is a function that accepts another function as parameters. To illustrate, we're going to discuss the map function. Okay, and so keep in mind that the function map already exists. Okay, you don't need to implement function map. But in my opinion, the best way to understand those higher order functions is to implement them. Okay, so I'm going to discuss an implementation of the map function, and that's going to be the only time when we're going to use our map function. After using just once, we will resume using the already defined map function. Okay, but once you implement the function, you will fully understand it, and it's best this way. So let's look at the implementation, this implementation of the map function. It takes a collection, an array, static array, and another function, okay? Well, this map function is very specific. It only works with collections of integers. Okay, the map function that comes with Scala is much better. It works with any numbers. Or actually with any types, to be honest. But in order to better understand how the map works, let's imagine this specific map function that takes a collection and takes another function. So this function that is given to map must have this signature or this specific type. So the function inside map is going to be referred as func. So func is the name of the parameter. The type is int, arrow, int. What does it mean, int, arrow, int?
or a function type. It takes an int, right, and returns an int, right? So that's the function that we need to pass to map, right? We're creating a new array called out. And the reason why we're doing this is because map is, it's not an in-place mapping, okay? Instead of changing the given collection, it returns a new collection, okay? So map is not an in-place function. So that's why we create a new collection here. We're gonna loop through each of the elements of the given array, okay? So from 0 until array length. When we use until, we don't include this index here. So from 0 to array length -1. At each iteration, we're going to call func, the given function, passing one element at a time from the array. The result of that is going to be saved in out. Okay? So for each of the elements of the given collection, we're going to apply the given function, right, doing a transformation. Then we have these two candidates for function func. First one is an increment, and this function increment takes a number and increments by 1. Returns the given number by one, increment by 1. This function here, as you know, increment, fits this profile, right? The signature. Takes an int, returns an int. Double also fits this signature, this profile. Takes an int and returns the number, the integer, double. So let's use these two functions and see what happens if I call map passing these two functions on the same array. So this is the array 38219, and we're going to call map, our map, passing the array and the increment function, right? A different way. Oh, this is using the given map function. And this is how you show the return array, and this is the double. So why don't you guys implement map function and see with your own eyes how a higher order function works. -7. Problem is the less water, right? I don't have a plan.
I went down my goal to sustain an elastic interface and finish.
So at the end, it becomes like just the ghost.
Yeah. My unfortunately, my cousin was reading last weekend. It was like this was 3:15. Yeah. So like and between 45.
Must be Chinese.
No. So now like South Yeah.
Sure to avoid Okay, so first time is just incrementing by 1, the other one is double. If we try to pass a function that does not take an int and return an int, doesn't fit the profile, like calling add, we get an syntax error because it's expecting type mismatch. It's actually semantic error, right? Because it's expecting int to int, and we're giving int, right, as a tuple to int. It doesn't work. As an exercise, I want you to create a lambda expression, so an unnamed function that does something different, like multiply by 3 or square. Try to do that. It has to be lambda. Oh, no, just call map. The function you're going to pass has to be yeah, you're doing something different, like multiply by 3. Pass this. So, data science classes, 7 to 8, 6 to 8. Yeah. Yeah.
That's, yeah. No, that's heavy. So that's a reserve. Five.
The syntax, right? You have to put inside the curly braces. Curly braces are not required. But I think you have to name the parameter. Try to use the name. Doesn't like it. Okay. So do whatever you want here. Squaring the numbers. Go all numbers squared. Okay. That was our map function. In order to use the provided map function, it's actually a method available in collections. So to switch this to use the given map function, you're not going to make call like this. You're going to call array dot map. Then you just need to pass the function. Okay. Now on, use collections map function. Okay. Any questions about the map function? That function is one of the big three, I think.
Starting to see why people like functional programming.
Ah. We're going to see functional programming in non-traditional functional programming language like Python and Java. They're adding those functionalities because they're becoming very popular. So Java, for example, supports some of these features. We're going to talk about those later. So let's talk about for each, similar to map, but doesn't return a new collection. So what's the big difference here? It's basically map in place, right? So for each is map in place. Why don't you change the implementation of our map function and make it as a for each. Okay, so just copy and paste our map function and make it a for each. What would you change in order to make the changes in place? Okay, so just remember, for each is map in place, making the changes in place, changing the array without returning the array. For each doesn't return.
Excuse me.
Okay. You're sad. What's that? Sad.
Submitted it a few times.
Wait, how many times did you submit it?
I kept catching bugs. I think I submitted like 4 times.
Can I
Okay.
Don't do that.
Don't do that.
Just keep the-
Keep the
We had a
last.
deal. Let's stick to the plan.
Did you end up being happy with your macros?
Yeah, man, I did Fibonacci. Keep the same.
Cool. There you go. I remember in an intro to engineering class for a CS major, they had me implement Fibonacci in C++, but they didn't they just had me copy paste the code and be like, oh, cool, Fibonacci, but didn't explain how or why it worked at all. So that probably would have been useful, but we got there.
If we can figure out how to incorporate an array, then we can do it the smart Fibonacci.
Dynamic programming.
Yes. Running outward.
Yeah.
You're doing that now, or you just?
We
Talked about it.
We talked about it. We've been doing a lot of
We haven't like fully implemented it ourselves.
Dr. Grant.
Yeah, what's up?
Ross here.
We like him.
Got our midterms.
At least you have midterms. Not about this one.
gonna review on Thursday, right?
Not defined it. So we have midterm next Thursday?
There's a schedule.
Yeah, that says midterm review,
Oh,
then
look at
midterm.
his guide on Canvas.
I know.
It's under the resources.
I have to make sure because, yesterday we were supposed to get a review and it really wasn't much of a review.
You scroll all the way.
Yeah, I have some
Yeah, that's
It's like a
better.
link that you probably share. It's functional at the very bottom.
Okay, so small changes here, right? For each, basically you don't need the out.
Okay, cool.
And you change array. And you get rid of this. When you get rid of the last out, the last statement, so your function is not returning any specific value, so the return becomes units. That's for each, so let's apply for each this array. So array for each increments. And we're changing the array, so now let's do double of that array for each double. Doesn't it feel kind of strange when you call the function, you pass a function first time? Really? Double? What is that? Double function? Okay, and let's do the last one. Just gonna remove those. And I'm gonna call array for each. I'm gonna pass our anonymous function. And let's print array again. Okay. What? It didn't work.
He's just.
I have a question. So I know what it is. It's not really Jesus.
Oh,
We have a array for each rather than array square.
I'm calling for each.
You're just
Should have called for each like this, right? Okay, let's try again. Our for each. Ah. Okay, so first one is incremented by 1, the second one is double, the other one is squared. Okay. It seems that the for each implementation in collections, right, is not doing what I said it was supposed to do. Similar to map without returning collection. Right, because we were doing array for each passing increment, and that didn't change the array, right? Yeah.
Because we need to look at the scala for each. Okay. So, sorry, my understanding was slightly different. It's actually the for each just takes one element at a time, okay, and do something with the element. But the given array remains unchanged. Okay, so essentially, if we're going to be strict in doing the exact same thing that the for each limitation from Scala's collection is doing, is basically just applying the function, but it's not doing anything with the collection, right? The collection should not be changed. So I'll make the corrections here. And this function should take a int, but shouldn't return anything, the units. Okay. So for these functions here, it really doesn't make sense to use for each. You will use for each, for example, if you want to print all of the elements, you would do something like print line, right? And, well, the function should take a value, right? And we're just gonna print that value. So this function takes an int and doesn't return anything, right? And we can also use our for each to do the same thing. So now using our for each to print each of the elements of the collection, you get the same thing. Okay? So slightly different than what I was saying here. I'll make the correction. Well, it doesn't return a new collection, but basically it applies the function, but I need to clarify that the function shouldn't return anything, so it should be unit. The next function is filter. So filter returns the elements that satisfy a given condition. Okay, so why don't you guys implement filter, and then we're going to use filter from the collection. Okay, just look at what filter is doing. The given function has to be a predicate function, so it has to return a boolean, and it has the condition that checks whether the element should be part of the new collection that you're going to do, and at the end you return the collection. Because we don't know the size of this array, I used the array buffer, which is dynamic.
And I'm using append to add the elements into this array buffer. When I'm done, I convert the array buffer to a static array. Just click Option and Enter to get the import for array buffer. Let's say we only want elements that are even. How would you do that? Using filter. Can you like this or more specific, more explicit? This function takes an int and checks if the number is even. Or you can just use wildcard. This expression can be used as your function. It knows that wildcard, it means the parameter for a function Okay, so we got only 8 and 2. And if you want to use Scala's filter function, filter method from arrays, you just do array filter and you pass the function. Same thing. Okay. So we already covered map. This is map filter. Garage is full. So fold. Before we do fold, let's do reduce left, reduce right. Then we do fold.
So reduce left applies a binary operation to a collection from left to right. So if there's nothing to reduce, just going to return 0. So the function passed to reduce left has to be a binary function, giving 2 numbers, reduced to 1. Okay? You're going to keep doing those operations, calling those operations. Eventually, you end up with just one value. That's the value that reduced left will return. So the first value is going to be, first value of the array is the seed, right? It's used to start. Then you're going to make calls passing the current value of the result and the next value. And keep doing that. Eventually, you will be done and you're going to return result. Look at this, it's a double marker, both sides. So when you're running out of black, it starts to become purple. So if you have 2, 7, 8, 1, and 3. So reduce result, right, starts with 2. And let's say that the function is just adding 2 numbers, okay? So you start with 2, and then you're going to call the function, right? You have the function call, function, passing result. So result currently is 2. Take the first one, and you're going to add result to the next element. Next element is 7, so you get 9. Right? So you're done. This 2. So next element is 8. 9 and 8, 17. Right? And then you have the next one is 1. 15. Right? We're basically doing a summation using reduced left. So 21 will be returned. Happens if you do subtraction. Why don't you get a piece of paper and do step by step and figure out that the result is negative 17. a string. We do subtraction. All right, so we have start with 2, and then 2 minus 7 minus 5, minus 5 minus 8 minus 13, minus 14, minus 17, right? Let's use arrays, collections, reduced left, just to make sure we get the same result. The same thing. Okay. So the reduced left function applies the binary operation from left to right. This is the order. 2 minus 7, right? Minus 8, minus 1, minus 3, and minus 17. There's also the reduce to right, which applies the binary operation from right to left. So the seed becomes the last element, right? And you're going to do before last minus, if the operation is subtracting, you're going to have 1 minus 3 minus 2, then 8 minus 2, that's 10, 7 minus 10, it's negative 3, and 2 minus negative 3, it's 5. So why don't you, I don't have the reduced right implementation, but let's just use reduced right. And let's use subtraction just to check our answers. So we get 5, okay? Check. Of course, for addition, it doesn't matter if you go left or right, right? But for subtraction and other types of operations, you can get different results. So those functions are available. There's no need to write them. You could have just used reduce left. This is how you use it. You can use reduce left with any type of collection, not only numerical ones. We can use, for example, reduce to implement make string. How would that work? So basically, you get 2 strings, and by using concatenation is a binary operation, right? You have 2 strings, the result of a concatenation is 1 string. So you are, in that sense, reducing, right? 2 to 1. So if you do reduce left, well, because reduce left, you need to specify that you're working with strings. So this is how you do specify that the values will be string. So Scala will know that you're doing concatenation. You have the first time, you're going to get Janet, and then second call, actually the first concatenation will call Janet, Bob, it's a comma in between. And then the third call, the second iteration, will concatenate whatever you had. Janet concatenated with Bob, you concatenate with Sandy. So basically you're doing reduce left just to make a concatenation, putting a separator in between, just like make string is doing for us. So similarly to reduce left and reduce right, Scala also defines fold left and fold right. So basically, the difference between fold and reduce is that fold is more generic because it accepts you to set an initial value for the operation, right? Because when I was doing reduce, remember that I picked the first one to be the seed, how I was going to initialize the return value result. With fold, it doesn't work like that. You have to specify the initial value. If it's a summation, for example, you may want to set the seed to 0. If it's a product, perhaps you want to do 1, something that is neutral, right? So basically fold is more generic because it allows you to set the initial value for the reducing operation. So this initial value is not actually referred as seed, it's referred as accumulator. So the accumulator is the initial value. With fold, you can set the accumulator. With reduce, it assumes that the accumulator is going to be the first element of your collection. So in functional programming, folding encapsulates a pattern of recursion for processing lists. Okay? So the folding functions use current notation. And we already saw current notation. This is basically saying that you don't have to name the functions when you pass to map and higher order functions. You can use unnamed functions. You already saw we were using those things. So the fold, when you say fold, assumes that is fold left. Okay, so if you just call fold or just reduce, assume that it's fold left or reduce left. Okay, so we have the 3 tenors here, map. So just as a recap, map applies a given function to a collection, but returns a new collection, right? We also saw for each, which applies the function to each of the elements, but it doesn't change the given array or the array where it's being applied. The function shouldn't even have the need to return a value, right? You can just make an operation on each of the values one at a time. So basically, you're doing a loop on each of the elements and performing something on each of the elements of your array. Then you have filter, which also returns a new collection, but it will apply a predicate function to filter the elements of the collection. And then you have fold, which basically applies a reduction function from left to right and allows you to set the accumulator, the initial value of your reduction. When we say reduction, reduction is a binary function that goes from 2 values to 1 value. So it allows you to reduce a collection to a single value. Okay? So on Thursday, we're going to practice. I have a list of functions for you to implement, and some of those functions will require you to use, for example, one of those functions that we discussed, like map, and those higher order functions. Always think about ways to use those functions to reduce your coding. And start thinking as functional programming, using the functional programming tools to find solutions to problems. So the next class, we're going to
gonna give you a list of problems to solve. You're gonna try to apply function programming to solve those problems, okay? All right, see you guys next time.